Thanks again for the introduction. Yeah, thanks for returning also to the second part. I did not finish my introductory lecture, so let me try to finish it quickly and then start with lecture 2, where we will talk a bit more about the mathematical foundation. Just to very briefly remind you, I tried to convince you that in order to understand the physics of such a two-dimensional electron gas in such a Hall bar in a magnetic field, and in particular to understand the relation between an applied Hall voltage and the transversal Hall current, we will look at that actually in these kind of systems, due to screening, we will see regions like here in this zero-dimensional model, where we have regions with constant density and integer filling of Landau levels. That to understand the physics within these regions, it makes sense to look at infinitely extended gapped quantum systems of fermions on a left. Okay, so what we will think of are infinitely extended systems of fermions with short-range interaction and a gapped ground state. So this is the initial state of the system, and now we would like to understand how such a system responds to applying a voltage, a Hall voltage or a Hall current, and to understand, and this relation would like to understand very precisely, so we have to make a clear definition or define a clear mechanism how we compute this response. And for this, I would like to give you some intuitive examples first. So let's first ask the question in a much simpler context, let's say for a hydrogen atom. So a hydrogen atom has also a gapped ground state, and the question is how does it respond to applying an external electric field? What will be the state of the system after we turn on an electric field, constant electric field, a small one, so epsilon will be here the gradient of this function, this potential. The epsilon is the strength of the electric field. So actually, if you, I didn't even explain this, so this is the spectrum or a sketch of the spectrum of the hydrogen atom. If you add to your Hamiltonian this constant potential, I'm again stuck with this here, this constant, this linear potential. What happens to the ground state? It will turn into a resonance because the spectrum of the Hamiltonian will suddenly fill the whole real line. There will not be a ground state for this system anymore. You turn it into a resonance. So in this case, we would say, of course, if I apply an electric field to a hydrogen atom, the ground state will turn into a resonance. From a spectral point of view, that's in a sense a big difference, but actually the state will be very close to the original ground state. It will only change very little. And a resonance is a state that has, if epsilon is sufficiently small, is basically as good as a ground state. It will be invariant under the time evolution for very, very, very long time. So exponentially long times in 1 over epsilon, because to change, it has to tunnel through this potential barrier here, and that might take extremely long. And basically, the same intuition is true for extended system. This is a sketch, and let me be very brief about this. Let me maybe not even explain it. Let me just explain this picture to save time. If we now think about gapped insulator, so an extended Fermi system with a gapped ground state. So this is in a non-interacting picture where we just fill these lock bands. Then basically, locally, every electron should more or less experience the same situation as the ground state of a hydrogen atom. There will be unoccupied states available with the same energy, but to go there, it has to tunnel a very long distance. but locally it will still see a gap in the energy landscape. So what we expect that also in that case, if we turn on an electric field, the constant electric field over all space, it will immediately close the spectral gap, but the system will evolve into a very long-lived, non-equilibrium, almost stationary state. Okay, but of course now that will be the goal, to prove this, that this really happens, and then to analyze these states into which such systems develop if we turn on such kind of perturbations and understand what currents are flowing in these states. Okay, so this is the heuristic picture which we want to fill with more mathematical precise data. Okay, now one thing is to show that there exist these kind of resonances or many-body resonances. The other question is, how do we justify that this is the right state to use to describe this experiment? So, in one way, this is, so to say, the standard way in response theory is to say, okay, what we really would like to model is the situation that we start in a given state and then turn on the perturbation dynamically. This is called adiabatic switching. And this is, so to say, what we would like to also take as a definition of the right non-equilibrium state we would like to analyze later on. So modeling the switching process means that we start with an Hamiltonian, or in our many-body setting with an interaction generating a dynamics on this quasi-local algebra, H naught, which has a gap to ground state, and then we turn on a perturbation, let's call it phi, and we turn on a small perturbation, epsilon times phi, so epsilon will always be small as usual, but we turn it on in a time-dependent way. So f will be a smooth function, and the idea is, let me press this button, I'm sorry, it will take forever, and okay. So there are different possible or natural choices for this switch function f. Okay. One is, which is used in standard linear response theory, is just an exponential function. And then you evaluate the solution of this equation at time 0 when, so to say, when the perturbation is fully turned on, when f has the value 1. Another approach, which I will explain, is to turn on the perturbation smoothly in such a way, and then to evaluate the solution of this equation at any positive time. What we expect is actually that if this picture I showed you is correct, that the solution to this equation will be constant once this f function f is constant again. Or, and that's the third possibility, which is used a lot in this community of explaining quantum Hall physics, it's charge pumping. We just turn it on and off again and see what kind of charge we transported in this process. Okay. So actually, if we would do it this way, the results we get would depend on this function f. Okay, we would not get a universal response, and that's why people use adiabatic switching, which means that we do this switching process very slowly. Okay, and this is called adiabatic switching, meaning we now scale this Hamiltonian in time with a small parameter eta, which I call the adiabatic parameter, in this way. That just means in this picture, I rescale this function by eta, so the switching happens on a time scale of order 1 over eta, so over a very long time scale. Or the pumping happens slowly, and the hope is that if we take eta to 0 or eta very small, we get results that are independent of the switching function f. Okay, then what we would like to define is the whole conductance or the whole conductivity. So what we will do is the perturbation we will switch on will be, for example, a constant electric field. And the response we're interested in is the current response. So actually, when you do standard linear response theory, and this then leads to a formula which is called Kubo's formula, what you do is you use such a switching function, and then you compute the expectation of the linear coefficient of the current response. So let me just, I will explain in detail what this is. Let me just say J is the current operator, or operator giving a kind of current density depending on the situation. Omega is the initial gap ground state. So omega composed with the time evolution generated by this Hamiltonian. This is the state at time 0 if I start at time minus infinity in the gap ground state. So this will be the state under this evolution at time 0, and at time 0 I evaluate the current. And my expectation is, of course, that the current is linear in the epsilon, which is the size of the perturbation. So I divide by epsilon, take the limit epsilon to 0, so I get the linear coefficient of the current response at 0 field. That is called the linear response coefficient. And actually, to get a universal expression, I take afterwards the limit eta to 0. So this is standard linear response theory that leads to Kubo's formula. And this is usually taken as the definition of the whole conductance. If we want, and this is something we want to do, we don't want to understand only the slope of the law that connects J and U at 0, but we want to at least get something in the direction of Ohm's law to show that this is really a linear function and also only has a derivative at 0. We use this Neas approach here. Oh, let's press again this button. Oh, and in this case, what we actually do is we compute really the current at any positive time here. And the state where we arrive after this smooth switching. And what we hope is that, I mean, we don't take the limit eta to 0, we take eta on any scale that is somewhat small compared to the perturbation. So actually we will see here we can take any positive power of epsilon, and independent of which power we take here, we will arrive here in the same almost stationary state. And then we have really for not only at epsilon 0, but at least for small epsilon function that gives us the current density as a function of epsilon, and we will analyze this current expectation here. Okay, and in the charge pumping, maybe very quickly, I mean, I will not go into this, but this is something which is often used when people analyze this problem on a torus geometry where you cannot apply an external field. They look actually at the change of the charge in a certain region. So Q is just your name for a charge operator before and after the pumping in one pumping cycle. Okay, and in these, there you will never see an epsilon and an eta. They will always put this same. So it's not so easy to actually, if you look at these papers, to discover this picture here, but that's exactly what they do. There's a question? Exactly. Exactly. This leads to different definition of the whole conductance. Or let's say, but they will be always all the same in the end. Okay? The numbers I get here for the whole conductance will all be the same. It's universal. So in a sense, if you're interested in the numerical value, it doesn't matter what you do. But this will not allow you to justify Ohm's law. It gives you the derivative at 0 of the function J of U. This will give you an average current over one cycle. And this will give you actually the possibility to evaluate the function j of u on an interval around 0. I will come to this in more detail. This is just motivation. So, but yeah, exactly. These are different definitions. In the end, if you look at the slope of this function, it will always be exactly the same. But one point was, of course, the switching. How we do exactly the switching should not play any role. This should be built in the definition that this is independent of X. Okay. Yeah. I will show you in a second what we can prove, and I would say this is at least a step towards Ohm's law. Okay. So I mean, this will be one thing we will talk about in more detail. So let me be very brief about this. So what we can show is that if our Hamiltonian, now in the setting I explained a little bit last time, is such an interaction with super polynomial localized terms, and it has a gap ground state, and the perturbation we turn on is of the form anything which is again a sum of local terms, doesn't matter what it is, and a linear potential, a linear external potential. I will say exactly how this looks in the many-body setting later on, but think of this xj being a linear external potential in the jth direction. If we turn on this adiabatically, then actually the solution of this corresponding Schrödinger equation, which is here, for all times after the perturbation has been turned on, is close to a state which does depend only on epsilon, and it's invariant, and this is what we call these non-equilibrium almost stationary states, up to terms that are smaller than any power of epsilon, so asymptotically small. So tested against sufficiently local R. So this should not be an A0, this should be an A infinity. Okay, but it doesn't matter. A0 is also correct. Okay, so that means this basically says there are these states which are almost invariant under the dynamic. You should think here epsilon is arbitrarily small, so they are invariant for a very long time, and they are reached by this adiabatic switching procedure. I will show it. In this bound, there is no, we cannot see delta. They are actually physicists who discovered this after us independently. They did not look at this adiabatic switching, they just constructed these resonances. They showed that they exist in quantum string systems under additional assumptions. And there you see actually you get a stretched exponential here instead of any power. So better estimate. And there the gap appears in the exponent explicitly. No, I mean, it's an hypothesis I need in the proof, but the size of the gap does not appear here. Ah, sorry, I misunderstood the question. Yeah. No, you will maybe not, you will not see it here because you will not be here the whole time. But so to say that we cannot keep track of the constants in any sensible way. So of course you could keep track of the constants, but then I would probably fill the whole page here and you would not see anything. So, but it's expected actually that the gap appears here, that the lifetime of this here in the stretch exponential exponent, you will see the gap. The larger the gap, the longer the lifetime. Okay, and now the question is, okay, so this is the existence of this near state, which we would like to understand, and now maybe let me be brief about it. So also in the literature, and I will also show you different results, people consider different kind of external perturbations to understand Hall conductance. either they apply potential steps, so that means our perturbation is the characteristic function on a certain step. So we just apply one potential step along one line in the sample. That's a potential step of size epsilon. This will give rise, as we will see, to currents flowing along this potential step. Or we do what I suggested before, we apply a potential gradient, so a linear potential, which will induce a current density in the whole, everywhere in the sample. And the response observable is either the currents along this line, and we observe the currents through a horizontal line, or we compute the current density everywhere. Okay, maybe this is not important here. What I wanted to emphasize is that these situations are physically quite different, because applying such a perturbation does not close the spectral gap, or at least we don't expect it to close the spectral gap. For general interacting systems, it's very hard to show, as I explained last time, but we expect that such a perturbation will not close the gap. So actually the corresponding near state is now the ground state of the perturbed system. And in particular, the response will be microscopic. So this will be really a microscopic current flowing here. So this will not model what we expect in real Hall insulators, where I told you that the potential difference between the two sides of the bar is orders of magnitude larger than the spectral gap. So this will allow us to compute the macroscopic current response, which is relevant for the experimental situation. Okay, let me skip this in the introduction. So one theorem which I would really like to prove to you, because later on, maybe tomorrow, because it has a very nice and elegant proof, I would say, is this result, which now takes for granted that this near state exists and is unique for such a kind of gap Hamiltonian. And the result, as it is published now, is only true for it's only proof for periodic H naught. But actually, I will also tell you how to generalize it to non-periodic. And it says the following. So we start in the gap ground state. We apply a perturbation where V is completely arbitrary and a linear but bounded, locally bounded. And X1 is a linear potential in the one direction. Then the current density, which is so to say here by this bar, I indicate the current density in the one direction is close to zero. It's smaller than any power of epsilon. That basically tells you that a gap system is an insulator. There will be no current flowing in the direction of the electric field. This is basically what this picture I showed you before, the heuristic picture, which was a one-dimensional picture, shows you. No matter how you tilt this band, the electrons will not be able to move. And basically this is a proof that even if you apply voltages on a macroscopic sample that exceed the spectral gap by many orders of magnitude, you will not see a current flowing through the system. And the second statement is that the current, the transversal current in the two directions, is linear in the applied field epsilon with a coefficient that we can, that has an explicit expression, but I'll explain what it means later on. And this linear coefficient is by definition now the whole conductivity plus terms that are smaller than any power of epsilon. B infinity I will explain later on. This is a class of interactions where the local terms decay faster than any polynomial. So basically, think of a many-body Hamiltonian like think of pair interactions that decay faster than any polynomial. This is, I say, Kuber's exact. This is what I would say. This is an approximation to Ohm's law. This tells me that around zero there are no power law corrections. So if I zoom in at zero, I see almost linear shape, meaning that once epsilon is small enough, I really have an Ohm's law. This is, yeah. And this is exactly also the same number you get from Kubo's formula, by the way. Yeah, yeah. But this shows more than Kubo's formula and something I could not show with the usual linear response approach. Okay, it's only introduction. This is the goal of explaining you this theorem because I think it's elegant. And so this is just the definition of this averages here, they exist. And I don't explain you now what this off-diagonal part is. And what I would like to emphasize is that this weakly interacting Hofstadter model I showed you last time, even for irrational magnetic fields, satisfies all the assumptions of this theorem. So we can apply it really to the weakly interacting Hofstadter model. And one more thing, before we come to the details, if we look at the thing, I mean, now I was making a statement about the current density. Okay, that's also not what you measure. You measure the current flowing through a macroscopic incompressible strip. So if I define here this observable, the experimental Hall conductance, I would look at the current J flowing through a, so to say, through a horizontal line of width L divided by the voltage drop over that line. That would be the experimental caricature of the experimentally measured quantity. And if I take the expectation in the near state of this ratio and take the limit L to infinity, I get again the Hall conductance given by the previous formula up to terms that are smaller than any power of the applied field. Why am I saying this? This is basically trivial. Why I'm saying this is that if I now look at the variance of this quantum observable, then actually I see that it's zero because it's really a macroscopic observable. Yeah, so there are no fluctuations. If I look locally at the current density, there will be quantum fluctuations. But since indeed, if they're far enough away, the points they're independent just basically by the law of large numbers, you will see no fluctuations for the macroscopic quantity. Again, this is something you can only prove if you look at a macroscopic response to a macroscopic perturbation. Yeah? Yeah. Yes, that's what I said for this. Here I assume H0 to be periodic. In my last lecture, I will tell you how to prove this if you drop the periodicity. So actually, okay, since this is not yet published, I wanted to be honest here, but it's a surprising thing, which I only learned myself a few months ago, that the gap condition alone enforces enough homogeneity so that this average here exists of the current density. So you need no further ergodicity or anything. The gap condition alone enforces to be the current response to be everywhere more or less the same. You will have fluctuations, but the averages exist and you get always the same value. Good, more on this later. So again, I mean, this is again what I meant by Ohm's law. So this quantity here has no power law correction, meaning that what you experimentally do, you are somewhere on this curve. So actually, you try to be on this curve as much far away from zero as possible, because that will allow you to control very precisely your errors. We have very precise error estimates or experimental error bars, while the usual linear response gives you the slope here at zero. And so it's important to have this statement here that tells you basically that you're not too far away. This applying Ohm's law at this point gives you a very good approximation of sigma h. Okay. Good. Another thing I would like to discuss is now, why is this Hall conductivity, I gave you a formula which I did not discuss, why is this so stable under perturbation? Yeah, it's like in many cases, like in this weakly interacting Hofstadter model, we will see it's even an integer. It's exactly an integer. Why is it constant under so many perturbations? The reason is because it's constant. It's really constant within so-called gap spaces. So if you change the Hamiltonian, you change the system without closing the gap, the whole conductivity stays exactly constant. This is a concept I would like to discuss, and all of this is not important. Okay, now this is because it mentions the work of Yeri. So the last thing of the introduction, and this is also something I will briefly discuss. So I told you that in this weekly interacting Hofstadter model, using the results of Yeri or Hastings or Dirac-Salmhofer, we can prove that the gap is stable if we add weak interaction to the system. But now the question is also the conductivity stable if we add weak perturbation. And this is actually what has been shown in this, at least from my perspective, really breakthrough paper at that time by Alessandro Giuliani, Vieri Mastrieto, and Marcello Porta, that the whole conductivity does not change when adding sufficiently small perturbations to a gap system using this rigorous renormalization technique. So to say, a small caveat is that they need to assume a form of periodicity that does not allow this to be applied to the Hofstadter model with irrational fields. So you get not basically the full picture here. And since irrational fields have been a huge thing in mathematical physics, at least here, I would like to add the statement that using our approach, we can actually prove that the whole conductivity, so lambda is now the parameter that adds a small perturbation, as I explained last time. So the whole conductivity does not change if we start here at a point in a gap space of the non-interacting model. Then there will be an open ball in R3 in this parameter space, that within this open ball, the whole conductivity is the same as here. So this follows from our approach. And actually, again, the one reason why we can prove this is because we immediately start an infinite volume where B is just a continuous variable. Doing this, I think we saw this yesterday in the talk of Fabrizio, approximating on finite volume quasi-periodic infinite volume systems is a very difficult problem. So if you start an infinite volume immediately, you avoid this problem. Okay. Now, so again, I took half an hour. So that was the course of that was the introduction. I wanted to do in 1 hour, didn't succeed. So now the next step will be to talk a bit about the mathematical tools we will be using, and then in lecture 3 or 4 and 4, I will prove this, show you the construction of these non-equilibrium almost stationary states, and then show you the proof of this last statement about Ohm's law, and whatever time we have, we will spend on additional topics. Okay. Good. But as always, you go on, interrupt me if you have questions. So now let me not redo this. This is was thought as a short recap. You all remember the Kerr algebra, we are on a lattice, and so on, the local algebra, the even and quasi and gauge invariant operators. They will appear, and if you have questions, I can repeat it whenever we are, whenever it appears, these concepts. Let me now, the next, really the fundamental insight in this kind of, or in this kind of system where our Hamiltonians have short range interactions is that physics really happens locally, and we want to quantify this. So we want to find ways of localizing observable, of localizing, no, not really states, but in a sense, yes, and understanding how long it takes so that the physics in different regions of space can, or processes can influence each other. So we want to get a better control on locality in these kind of systems. And to do this, I need to introduce a concept, which is called the conditional expectation, and which is the generalization of taking partial traces to these kind of systems. So morally, you can think of our Fock space on the infinite lattice as the infinite tensor product of Fock spaces on each lattice side. Okay, so think very roughly as of an infinite tensor product of Hilbert spaces, and a finite tensor product of Hilbert spaces, you know, you can take partial traces. And this we would like to now generalize to this infinite tensor product of Hilbert spaces. And this is done by the thing I introduced. And to define it precisely what it is, I have to first tell you that on this car algebra A, there exists a unique tracial state, a state which generalizes, in a sense, the trace to infinite volume. And it's tracial if it satisfies expectation of AB, expectation of BA for all A and B, so like a usual trace does. And it can be constructed, and maybe I don't want to go into this now. It can be constructed by just using the trace on finite domains, normalizing it. Oh, so this should be actually a 2 to the n here, not an n. Normalizing it in such a way that the trace of the identity on each scale is always 1. Okay? So this is called a tracial state, and it can be shown that there's a unique tracial state also in infinite volume. And now what one would like to define is map EM for any subset M of the lattice that takes an observable A and then takes the trace over all the factors that come from positions that are not in M. So we trace out everything around M. Okay? There's a quotation marks because this is not defined in a completely obvious way, and this should be then an observable completely localized in the region M. And to make this precise, one has to do a bit of work, and actually this was done in a paper by Araki and Moria in 2003. They prove that such a map exists. They show that there exists actually a unique map that takes the full algebra to the algebra localized over the set M. That has the property that the tracial state evaluated on AB, if B is supported in M, then this is the same as the tracial state evaluated on the conditional expectation of A times B. So if you write this down for the usual partial traces, you will recover that this is satisfied for partial traces. But this is now on the infinite level. And it has additional properties. In particular, it's a projection. I mean, it's even a more general property here. So if you have A and C in AM, so you can take any operator that is already supported in M out of EM, either to the left or to the right, or both. Okay? It behaves nicely under composition. So if you first restrict to M2 and then to M1, it's the same as just restricting to the intersection. And it leaves invariant the set of even operators. It leaves invariant the set of gauge invariant operators. And it has norm 1. So it has very, very nice properties you would expect from a partial trace on finite volume. So I will not go into proving this. This is just the tool we are going to use. How are we going to use it? The first step is now to define better how localized an element, an operator in this quasi-local algebra is. By introducing norms which have an index mu x. Mu tells us something about the decay, and x is a location in space. And it's very simple. We take just the operator norm of A, but now we add, what we look at is how good can we approximate A by restricting it with the conditional expectation to a ball of radius k around x. For practical reasons, we will use the infinity metric, the infinity norm. The maximum norm on ZB, so our balls are actually cubes. Okay? So we restrict to a cube, I would still call it a ball around x of radius k, and see how good does it approximate the original A. And what we do is we multiply this error we make by restricting A with 1 plus k to the nu, and then we take the sup over all k here. Okay? This gives us an idea how fast this A decays away from the point x. This actually really defines a norm on A, no, that's not different. If we denote now, here. Okay, so what we're going to do is we look at those A for which these norms are finite for all nu. These are the A that, I would say, sloppily decay faster than any inverse polynomial. And this set will be denoted by A infinity. Okay? So actually, if this is finite for one x, it will be finite for every x. It's like if you think of Schwarz space or whatever, it doesn't matter where you put the origin. Once it's, you can move it and it will still be, Schwarz function will still stay in Schwarz space. So A infinity are those observables for which all these norms are finite, and these norms turn actually A infinity into a Cauchy space. So we have a topology on this set. Okay, and why is this useful to have this concept? Let me give you one example lemma, which I'm not going to prove. The proof is a long computation, but it's very simple. Giving the information I gave you, it's the idea that if we have two operators that are localized in different regions of space, if they are strictly localized and one of them is even, they will commute. But now we have operators that are not strictly localized but somewhat decaying. So what we expect is if they're decaying fast and far away, they will almost commute. And this is exactly what this lemma tells you. So if you take two rapidly decaying operators here, and one of them is even, then you can estimate the commutator, this new norm of the commutator by taking the new norm of A at Y, the new norm of B at X. You lose a bit of decay. This is this number m, but then you gain an inverse power of the distance between the 2 points. Yeah, this basically gives you an idea of how to control commutators of operators that are not strictly localized, but well localized. Yes. No, this will also go to infinity. I mean, here this, for any operator where this is finite, there will be a minimal value for this. If you put the x where the operator is localized, if you move it away from where the local is, it will always be finite, but it will grow rapidly. So this will actually grow like y to the nu plus m. if you move it through. So actually, if you, yeah. So this is only a good bound if you know that A is localized near Y and B is localized near X, and these things are not too big. But it's always valid, but not very interesting if you take limits. But thanks for the question. Okay, good. So this is one tool we will be using, localization of, or almost localization of operators. And then the next concept I already mentioned, we will, our Hamiltonian, for example, will now be in so-called interaction. So here the name is really not in the sense of interaction between two particles, but the technical term people use, so I also use it. And this is a map, which is, as I said, I introduced it as a sum of local operators. But for technical reasons, in particular to use existing results, one defines it a little bit differently than I did last time in a more complicated way. So interaction is a map that takes finite subsets of ZT and maps it to operators that are gauge invariant in such a way that for each M, that finite set M, phi of n is an operator supported on n. Okay? And we also assume that all these operators are self-adjoint. Okay? And we also require, that will be automatically satisfied for our fast decaying interactions, that if we, for any M, if we sum here over all finite sets phi of k that intersect M, that this sum converges unconditionally. For us, it will always converge in norm. Okay, so this is some local finite net condition. And on the set of interactions of such maps, we define again norms that control how well localized the local terms of the interactions are. And again, for reasons which I might come into, we take a slightly different definition here. So we define the nu norm. So you should think again about the nu being the rate of decay. Let's first fix one x. For fixed x, we look at all finite sets M containing this point. So all sets interacting with that point. And we sum up the norms of the corresponding interaction terms phi of M with a weight, which is the diameter of the set M to the power nu. So the larger the set, not larger, so the larger the diameter of the set, the larger the weight. So basically for this to be finite, this has to decay, this norm has to decay like the diameter. Oh, actually, like faster than 1 power faster than the diameter, so that this is summable. No, this is a many-body interaction. Yeah, so M is think of if we have a two-body interaction between particles, then M would be a set of sets X and Y, and phi of M would be the product Nx times Ny with the corresponding potential. No, I mean, this name is also the hopping terms will be part of the interaction. So that's why the whole object is called interaction, and physically we would usually in a model only call parts of it an interaction. Yeah, exactly. Everything together, and it will be in the following. It can be also much more. There can also be three-body interaction, three terms, whatever. Just so to make clear that we are introducing a somewhat strange new name here. But this was not my invention, so this is a long tradition to call it that way. Okay. And then this is at point X, and then we take the soup over all X, and that will control the localization of the local terms of our interaction. And again, and now the Fréchet space of interactions where this is finite for all nu, this is the space B infinity. So that means in particular this kind of physical modeling where we have hopping and two-body interactions. The two-body interactions have to decay faster than any polynomial, and the hopping terms as well. Okay. Now I introduced this other notation last time with the phi x, this is also useful depending on what we want to do. And so what we can also do is we can try to sum up all interaction terms connecting to a certain point x and define the interaction at x. But to do so, we have to decide which m belong to the point x. And this is, somebody actually mentioned this last time, there's of course some arbitrariness involved. So what one first does, and this involves some arbitrariness, we define Rx to be the set of all finite subsets which have x as their center. You will be able to work out the definition of this, which is arbitrary, because now we are on the grid, so maybe you have to decide if you're on 1D, two sides, is it the left or the right? You have to make a choice. But you can make it, and it's completely irrelevant for what we're going to do, so I'm not going into this. But once you did this, you can sum up all the terms that belong to x and call this phi x. And actually, with what I told you before, this will be an observable or an operator in A infinity at x. So that will be really localized. Exactly. Exactly. And then I get a partition of all the finite subsets into sets that are located at a specific x. This allows me to now define the interaction at x. There is some arbitrariness, or maybe a lot, but it will be useful. In particular, it will be useful because this guy will be an element of the algebra, nicely localized near x, in the way I do it. Okay. And yeah, this is what I was just saying. So the new x norm of this observable will be bounded by the new norm of this interaction for all x and nu. And such maps that take points in the lattice to elements of the algebra, so here for every x we have a phi x, this is called in the literature zero chain. If you look in other papers, I will not use this notation. Ask me in the okay, I was just about ask me in the break about this. You can then, if you take commutators of such two guys, you will have objects indexed by two positions. This will what people call one chain, and it's asymmetric in the things, and you can try to do some sort of discrete differential geometry with this, but we will not do this. So it is useful, but we will not use it, or we will not need it. I just say this because people use this expression. Physicists. For example, Kapustin, not that I know, no. I think it's really the idea is it has some similarity to the usual chains you find in algebraic topology, but I don't think it's really a zero chain in the usual sense of homology theory. Maybe I'm wrong, but this is actually, I didn't find this anywhere. But you can, it's very similar. I mean, as I said, if you take a commutator of two such interactions, you will get something which is indexed by, and now I think you have a psi y and take the commutator, then you have y and x indicating these objects, indicating these objects, and it will be antisymmetric in x and y. So you will think of it as that. One point. Okay. Now, and the last thing, what I would like to introduce, we want to have these perturbations which are unbounded, in particular these linear potentials. This kind of objects, they are not interactions in the sense, because they are sum of local terms, but the local terms are not bounded. Okay. And in general, that's a problem to work with these things in infinite volume. So one wants to avoid this, but we want to have these unbounded potentials. So we introduce another concepts, so-called Lipschitz potentials, which are actually, one can think of them as interactions that are supported only on single sides, that don't couple different sides. So they are of the form that for a single side, they are a multiple of the number operator on that side. But this function, this multiple here, that can grow linearly. So what we require actually is that this function is just a Lipschitz function on ZD, meaning it is specified such a uniform Lipschitz condition. And Nx is the number operator inside X. So this is an external potential U of X. That is what we want to model. And okay. So let me just give you some things. I will not put all these lemmata. These are technical things, long computations, but in a sense straightforward, as you can hopefully imagine after what I said. What one can now show is, for example, that if we have such an interaction that is in B infinity, fast decaying, and a Lipschitz potential, then actually the sum of the two defines a derivation on the algebra. We can compute commutators with them, not with all observables. If they decay too slowly, these commutators may not be well defined, but if they decay fast, they are well defined. So for any A that decays fast, we can define the commutator of this interaction or Lipschitz potential with A by summing up all the commutators for the finite terms here. The idea is, or we do it differently, we do it on the set of change. We take all local pieces of this interaction or the potential, commute with A and sum over all X. The idea is, this is well localized. So for X far away from the support of A, this will decay so fast that it's summable. Okay, this you can show. So this means these commutators are well defined. And this allows us to define this derivation, the commutator of an observable with such an interaction as just the limit of these sums. Okay, we can, something that is localized, we can commute with something that lives everywhere and is not in any way summable or so, because the commutators of the terms far away will not contribute. Okay. And actually, if we think about this now in a more analytic way, the commutator with such a B and P infinity interaction is really a continuous map on this Bechet space in the following sense. The new norm of the commutator of A with such a rapidly decaying interaction can be bounded in terms of another norm of A and a norm of this interaction, or this is the Lipschitz constant of V and another norm of the interaction. So maybe the only thing here which is not totally obvious is, why can we also commute with these linear increasing functions? It's because we assume here that our A's commute with a number operator. So if I would replace this locally by a constant function on the support of the observable, the commutator would be 0, because it would be the number operator on that set. But on a sufficiently small set, this Lipschitz constant, so to say, differs from the constant functions only by something which is proportional to the Lipschitz constant, no matter where I am. So I really see in these commutators only the gradient of this function, the Lipschitz constant. Okay, good. I guess I should stop now. For next time, that tomorrow I will show you that also these kind of nice interactions will generate Heisenberg time evolutions on the algebra of quasi-local observables, and this will be the type of time evolution we will then analyze. But let me stop here and thanks for your